Welcome to your podcast for Lesson 35, Coefficient of Friction. After viewing the podcast, you should be able to state the variables that affect the force of friction, define the coefficient of friction, and solve problems involving coefficient of friction. So this ties into what we did in your friction lab, so be able to discuss what factors affected the force of friction. Alright, so what we learned from completing the friction lab is that the magnitude of the frictional force acting on an object depends upon two things. The first one being the contact material. So the type of material that the object is made of and the type of material that is sliding on makes a difference, and you saw that in the lab, whether it was just the wood block on the aluminum track, or whether it had sandpaper, or whether it had plastic in between it. So think of these two examples. A waxed snowboard will experience little friction against a powdery snow. So if you go skiing or snowboarding, you know it's very important to always wax your snowboard or skis to eliminate friction. You're going to be going down the hill much faster. And example 2, a waxed snowboard will experience quite some friction if you try and go down a surface that doesn't have snow on it, for example, paved asphalt of a road. And the second thing that you should have noticed from your lab is that the normal force also affects the amount of friction. So how hard the surface is pushing on the object is going to influence how friction acts on it. So a heavy crate sliding across a floor is going to experience more friction than a light crate. And you saw this in the lab. The more weight that you added on top of your wood block, you noticed the larger the angle you had to lift the ramp to get it to slide. Example 2, a crate sliding down a 10-degree incline is going to experience more friction than that same crate sliding down a 30-degree incline. That's because we know that the more that I slant that incline, or the greater the angle is, the less friction we're going to see. So the steeper incline, we're going to see objects accelerating faster. That's because its Wx component of weight is going to be greater, and friction is going to be less. When we do problems dealing with friction, we're going to have to now consider something called the coefficient of friction. And for every combination of two contact materials, there's a specific ratio that exists between the frictional force and the normal force. We call that ratio the coefficient of friction. And so you can see some common examples that we're going to work with here, and they're given values for the coefficient of friction. These values will be provided to you in your problems, but you can add these to your notes and also add them to your formula card for reference in problems, just in case it wouldn't be there. But you can see a lot of this makes sense if you have objects where we know there's little friction that exists. For example, between ice and ice or steel and steel, you see that the coefficient of friction is much smaller, 0.01 for the ice on ice and 0.07 for steel on steel. And you see a larger coefficient of friction if you have two surfaces that you know you're going to experience a lot of friction between. For example, rubber on concrete is going to have a coefficient of friction of 1.0. Now you'll notice that it's represented by this little kind of funny looking U. That's actually the Greek letter mu. Okay? So we'll use that to represent our coefficient of friction. Two new equations that you can add to your formula cards are listed here. They deal with the coefficient of friction. So one comes right from our definition, which says that the coefficient of friction is the ratio between our frictional force and our normal force, and so mu is equal to FF over Fn. The second formula that you see is essentially the same thing, it's just rearranged. So frictional force is equal to mu times normal force. First step to solve these problems is we're going to find our normal force first. And so the block of wood that we've been working with in class has been affectionately given the name of Fred. So we're going to solve for the coefficient of friction between Fred and the table if I push him along at a constant speed with a force of 10 newtons. And remember, Fred has a mass of 5 kilograms. So we know that when Fred is just sitting on the table, that 5 kilograms is going to be pulled by gravity, and that's going to give us an FW, which is equal to mg. We know his mass is 5 kilograms times the value of 10 for g, and that tells us that Fred's FW is 50 newtons. Now we also know that F net in the y direction is equal to 0, so that tells me that my normal force has to be equal and opposite to FW in this case, so that's also 50 newtons. Okay. I'm pushing Fred with an applied force of 10 newtons, so here's my applied force, and very important piece of information, because we know that Fred is moving at a constant speed, my F net in that x direction is also going to be 0. And so what that tells me is that my force of friction, which I know I would draw opposing motion, is going to be equal and opposite to my applied force. So in this case, that's 10 newtons. So that's what your free body diagram would look like. Now I'm solving for the coefficient of friction, so I'm going to choose this equation since it's already set up for me. I'm just essentially going to have to plug and chug. So remember, mu is equal to our force of friction divided by our normal force, which in this case my force of friction is 10 newtons, divided by my normal force, which is 50 newtons. Okay. And so when I plug and chug this, 10 divided by 50 is going to give me a coefficient of friction of 0.2. Notice the newtons cancel out, and you're not going to have any units for the coefficient of friction. All right, in practice problem number 1, I'm pushed downward with a force of 100 newtons and to the right with a force of 50 newtons onto a 1 kilogram book that's at rest on the table. The book moves at a constant speed. So again, we're going to be solving for the coefficient of friction between the book and the table. So let's draw our free body diagram here. We know that I'm going to be pushing downward with a force of 100 newtons. And we know that this book is a 1 kilogram book, so it's also going to have an FW. And again, FW is equal to mg, so 1 times 10 is going to give us 10 newtons for our FW. I'm also pushing to the right with a force of 50 newtons. So we'll call this applied force 1 and applied force 2. And we know that that book remains at rest. So again, that tells us some very important things. We know that I now have two forces, FW and A1, my applied force 1, going in the downward direction. So that means that my normal force has to be equal and opposite to these two things added together. And so 10 plus 100 is going to give me a normal force of 110 newtons acting in that upward direction. I also know, because it's at, or now moving at a constant speed rather, that my frictional force is equal and opposite to my applied force of 50 newtons. And so that tells me that FF is equal to 50 newtons. All right, I'm going to use my new equation. So mu is equal to the force of friction divided by the normal force. Okay. And in this problem, it's going to be 50 newtons divided by my normal force of 110 newtons. And when I plug and chug this into my calculator, I'm going to get 0.45. And again, newtons will cancel out, and so I don't have any units for my coefficient of friction. In practice problem 2, I'm lifting upward with a force of 5 newtons on that 1 kilogram book, and so I know I'm going to have an applied force of 5 newtons on a 1 kilogram book. So what that tells me, again, remember that's equal to my mass, so I'm going to have an FW of m times g, or 1 times 10, so 10 newtons, and it's at rest on a table. With what additional force do I need to press onto the side of the book to make the book move at a constant speed? So we know there's going to be some applied force here, okay, and we'll just call this one applied force 1 and applied force 2, but I don't know what it is. Now I do know that it's moving at a constant speed. So remember, a constant speed tells me that my frictional force, okay, FF, has to be equal to whatever this applied force ends up being over here. So FA2. The other thing that I know, because it's at rest on the table, my normal force has to be equal and opposite to my FW. So if my FW is 10, but I've got one applied force here pulling up of 5 newtons, that means that my normal force has to be acting upwards as well, also with a force of 5 newtons. Okay, because these have to cancel out. So 5 plus 5 is 10 in the upward direction, and that cancels out the 10 in the bottom. Okay, we're acting towards the earth. This time I know my value of mu, so I'm going to use my rearranged version of the equation. So my force of friction is going to be equal to mu times my normal force. My value for mu is going to be 0.2, and my normal force is going to be 5 newtons. Okay, and so I multiply these two things together. 0.2 times 5 is going to give me a frictional force of 1 newton. Since we know that it's moving at a constant speed, that frictional force of 1 newton, remember, is also equal to whatever that applied force is that I would need to push the book with. In this problem, we're pushing that 1 kilogram book against the wall with a force of 100 newtons, and it's being held at rest. And so we know that 1 kilogram book is still going to have an FW of m times g, or 1 times 10, so 10 newtons. And I'm pressing against this book with an applied force of 100 newtons. And so this time our normal force, right, isn't going to be opposing our FW, but it is perpendicular to the contact surface. And that tells me that my normal force is going to be acting, in this case for the drawing, towards the left. Because that book is at rest, I know that it's going to be equal and opposite to my applied force, so Fn is equal to 100 newtons. The other thing that I know is the book is at rest, so what that tells me is that my force of friction has to be equal and opposite to my Fw, which we solved to be 10 newtons. Okay. So to find the coefficient of friction between the book and the wall, I'm going to use mu is equal to my force of friction divided by my normal force. My force of friction is 10 newtons, and my normal force is 100 newtons. And so when you plug and chug this into your calculator, you get a value for your coefficient of friction being equal to 0.1. So here's a bonus point opportunity for you. You can get 3 points if you can tell me the acceleration of Fred if the coefficient of friction between Fred and the floor is 0.2 newtons.